Welcome back to ME 760 Engineering Analysis 1. We just continue what the business that we used to do last lecture. Last lecture we talked about some special matrices, which are the complex matrices, and we showed that the eigenvalues for eigenvalues for some of those matrices, like the Hermitian, skew Hermitian, normal, and the unitary matrices. We showed that for Hermitian, for example, it is real numbers, and for skew Hermitian they are a zero or pure imaginary, and for unitary matrices this is just the amplitude of lambda square is equal to 1. Today we'll just give a theorem, and then we'll move on to discuss the rest of the properties of normal matrices and why normal matrices are important. Because normal matrices, they are a class of matrices under this normal umbrella. You will find that you will have the Hermitian, skew Hermitian, and unitary. And the Hermitian, skew Hermitian, and unitary, they are complex matrices. And if you take the real counterpart of those matrices, you will notice that the Hermitian, what's the equivalent for the Hermitian if the matrix is completely real?
Symmetric.
So it's a symmetric. And what's the skew Hermitian is what? Skew symmetric, the counterpart. And the unitary is the counterpart of the unitary if the matrix is real is what? Orthogonal. Yes? So now we will continue the business for last time, and we'll give a theorem here. And the theorem states that the eigenvalues of normal matrix, and again the normal matrix, they have 6 submatrices that represent those normal matrix, and we just stated those 6 submatrices are the complex conjugate of the Hermitian conjugate matrix. So in order to prove this, let's assume that we will have the characteristic equation for the matrix A, and this is just the determinant of A minus lambda I, and this is equal to 0. So this is the determinant. The characteristic equation is just A minus lambda I all operated over x equal to 0, but the characteristic equation is just this one. So this is A minus lambda I operated over x equal to 0. We will call this matrix here matrix B, for example. So this will give us matrix B operated over vector x equal to 0. Then in principle, if we take the adjoint for this matrix, this is Bx, and I will take the adjoint, and this will give me, if you take the adjoint of 2 matrices, for example, when you will take the property for adjoint, you will notice that you will have x adjoint first, and then B adjoint, and again this is equal to 0 because the adjoint of 0 is just 0. So let's call this is equation 1 and this is equation 2, and then multiply equation 1 and equation 2 all together. So when you do this, you will have the adjoint x adjoint B adjoint multiplied by Bx, and this is equal to 0. So what's B adjoint B? From here, we define B to be A minus lambda I. So B adjoint B is just nothing more than A minus lambda I adjoint for B adjoint multiplied by B, which is A minus lambda I, just direct substitution. Then when you have this, you will have the following. So to get the adjoint for this matrix here, this will give you A adjoint minus, what's the adjoint of a number? It's transpose, then take the complex conjugate. But transpose of a number is a number, so it will be the complex conjugate of this number. And again, unitary matrix, the adjoint of the unitary matrix, when you rotate it, it will be the same. And the complex conjugate of 1 is still 1, so it will be still the same I. You do not have any change. And this is A minus lambda I. Then when you do the multiplication here, this will give you A adjoint operated over A minus lambda conjugate operated multiplied by A minus lambda multiplied by A adjoint plus lambda adjoint. So we stated that the matrix is normal. So for normal matrices, we have the following property. A adjoint multiplied by A is equal to what for normal matrices? For normal matrices, the multiplication of the Hermitian adjoint by the matrix will commute. So the matrix will commute means that you can flip the order. And this is one of the nice features of the normal matrices is they commute. Generally, matrices do not commute, but for normal matrices, the property is they commute. So when you apply here the commutation property here, you will end up with, we can replace this one, so this will be A dagger minus lambda star A minus lambda A star plus lambda star, and then I can rewrite this as A minus lambda I multiplied by A minus lambda I dagger, and what's this? This is what? B, and this is what? So B dagger. So we reach to P dagger B equal to B dagger. So what does it mean? It means that B is what? Is normal matrix. So what's B? Is also normal. So now if we call this one 3, so from 3 we have X dagger, B dagger, Bx, and this is normal. this is normal, so I can swap the order for commutation. So X dagger, B dagger multiplied by X, because they are normal here. So just I did the opposite. Then we can take this 2 and make it as X B dagger, or the reverse, B X, and this is dagger and dagger. And this is the property that if you have a joint of a multiple of multiplication of matrices, when you expand those, you will bring the last one first, then the first one last, and this is this property. So we applied this property, and then you will have B dagger X, and this is equal to 0 because 3 is equal to 0. Then what's happened is, if we have B dagger X, the adjoint of this multiplied by the same matrix is equal to 0. What does it mean? So a vector, let's say B multiplied by X is a vector, and the same vector, if you take the adjoint, the Hermitian adjoint, is equal to 0. So it means that B dagger X itself is equal to 0. And if this equal to 0, what's B dagger? It's A dagger minus lambda star I operated over X equal to 0. What we will get from this? That the eigenvalues of what? Of the Hermitian conjugate. The eigenvalues of the Hermitian conjugate is just equal to what? Are complex conjugate of those of A. And this is the theorem. So the theorem states that if you have a normal matrix, yes, the eigenvalue of the normal matrix, the eigenvalues of the normal matrix A will be the complex conjugate of the Hermitian conjugate. So it will be the complex conjugate of the Hermitian conjugate. Yes? So the eigenvalues for the Hermitian, so if you have a normal matrix, let's assume that I give you a normal matrix, a matrix A, and I said the matrix is normal, and you want to get, for example, the eigenvalues of A. So you can say, okay, I will get, there is one way is, you said, I will see what are the eigenvalues for the Hermitian conjugate. So this is the Hermitian conjugate. You get the eigenvalues for this Hermitian conjugate is just the complex conjugate of the original matrix. So let's assume that you have a matrix A and you calculated what are the eigenvalues for this matrix A. Then there is no need to calculate the eigenvalues for the Hermitian conjugate. So the theory said if you knew what's the matrix A and you knew what's the Hermitian conjugate, for example, so once you calculated what are the eigenvalues for the matrix A, take the complex conjugate of this, and this will be the eigenvalues for the Hermitian conjugate matrix. That's it. And this is what we proved here. So now, and this is again a property of the normal matrices. You have a matrix, you got the eigenvalues for the matrix. If you have the Hermitian conjugate, the eigenvalues for this Hermitian conjugate matrix will be the complex conjugate of the original matrix A eigenvalues. So let's now look at the eigenvectors. So last lecture and part of this lecture we looked at the eigenvalues for Hermitian, skew Hermitian, unitary, and then we look for the normal matrix. Then let's look for the eigenvectors of a normal matrix. So eigenvectors of normal matrix. Let's assume that we have two eigenvalues for the equation AX, we'll call XI equal to lambda XI. So we'll have two eigenvectors, Xi and Xj. And AXJ is equal to lambda J Xj. So you have two eigenvectors and two eigenvalues for this matrix A. So let's call this equation number 1, and this is equation number 2. If I multiply equation number 2, multiplied by the Hermitian conjugate, which is for the vectors, eigenvectors xi, I call it x dagger here, and I multiplied by equation number 2. So this will be xi dagger a xg, and this will be just xi dagger, what's a xg, lambda j xj, and I call it 3. Then we'll take again this part here, x dagger a xg. Again we'll do the same trick. I will reverse the order, so it will be a dagger multiplied by x, and I take dagger here. So all of you know this trick again. This comes from the property that if you have a b g dagger is equal to what? G dagger b dagger a dagger. So this is the property here. Okay, guys? So this is xi, and this is xj. Now, if we have a dagger xi, we just stated 5 minutes ago the theorem. Theorem said what? What will be the eigenvalues for the x dagger, the a dagger? So it will be lambda what? The complex lambda multiplied by what? Xi. Yes? And this is dagger xj. So what's this? If you expand it, what's the Hermitian conjugate of a complex number? it will give you the same number, because you take the rotation is the same number, and you take the complex conjugate of a complex conjugate will return back to the same number. And this one will be what? Xi dagger, and this one is Xj, and let's call this 4. So this is lambda, this is lambda I. So from 4, lambda I, Xi dagger, Xj is just equal to lambda J Xi dagger Xj. And this is from what? From here, from 3. Yes? Because this term here is equal to what? This term here. Yes? So this equation and this equation, the left hand side are the same. So this, the right hand side, should be equal to this one. So Xi lambda I Xi dagger Xj should equal to this one, which is lambda j is a constant. I will take it outside, multiplied by Xi dagger Xj. What you will understand from here is take this right hand side to the left hand side, so this will give you lambda I minus lambda j, all multiplied by Xi dagger Xj, and this will be equal to 0. But this is for matrices. So if we are talking about linear vector spaces, and matrices are elements of linear vector spaces, how can we write 2 vector matrices like this? How we write this? This is the inner product of the 2 vectors, because this vector will be just the transpose, and then you will multiply it. So those are the inner products of those 2 matrices. So this is equal to what? 0. So if lambda I is not equal to lambda j, what does it mean? If lambda I and lambda j are not equal to each other, so this term will be what? Non-zero, multiplied by something equal to 0. So what does it mean? The inner product should be equal to 0, and this means that Xi, Xj are equal to 0, the inner product. What does it mean? Orthogonal. So the eigenvectors are what? Are mutually orthogonal. So for a normal matrix, we notice that the eigenvectors of a normal matrix form an orthogonal set of basis vectors. So if you have a normal matrix, you can easily find a set of normal orthogonal unit vectors, or bases in this case. Okay, guys? So this is just when we talk about 2 of the eigenvalues, lambda 1 and lambda 2. So if we have n eigenvalues, so if all n eigenvalues of an n by n matrix. So we knew that the n by n matrix will have n eigenvalues, and if all those n eigenvalues are distinct, so not two of them are similar, they are all of them are distinct, then all the eigenvalues eigenvectors are mutually orthogonal. So this is a very important property of orthogonal of normal matrices. And of course, normal matrices means Hermitian, anti-Hermitian, and unitary, and also skew, symmetric, and symmetric, and orthogonal. So if you find matrices that are normal, one of the very important properties of those normal matrices is if you have for those normal matrices all the n eigenvalues are distinct eigenvalues, then the corresponding eigenvectors represent a mutually orthogonal vectors. So you can take them as what? As bases for the matrices or for the vector space. What does it mean that you will take them as a basis? You can represent any vector in the vector space using those vector bases. Like in the x, y, z, in the three-dimensional Cartesian coordinates, they are mutually orthogonal, and I can form any vector based on those three vectors I, j, k. So, and later on, when we move on to in the course on let's say the functions, we knew that linear vector spaces are not only composed of matrices, but it can be composed of what? Any elements, functions, or operators, or let's say a Laplace transform, or something like any integral transforms. So we will note that the normal matrices can be transformed to normal functions or normal operators, and we will know that for normal functions or normal operator there is set of orthogonal functions or operators or matrices or vector eigenvectors that we can use later on in the course. So what if the eigenvalues are not distinct? So there is some of those eigenvalues are similar. So in this case we will call it a degenerate case. Like in quantum mechanics, when you have a degenerate solution, in quantum mechanics when you solve the Schrödinger equation, you usually will get the eigenvalues and eigenvectors, and your eigenvectors will be what? The wave function. And if you take the amplitude square of the amplitude of the eigenfunction and you just integrate over the whole space, this will give you the probability of finding the particle inside this space. And the eigenvalues will be what? The energies corresponding to those eigenvectors. And if you have an eigenvalue, let's say similar eigenvalue for the same eigenvector, what does it mean? It means degeneracy. Yes, that you will have similar for the same eigenvalue, for example, which is the energy. For the same energy, you will have several let's say several eigenfunction. So this is the case here. So if we have if any lambda i's are equal, we have a eigenvalue degeneracy. What do we mean by eigenvalue degeneracy? Let's assume or suppose that we have k's we have n eigenvalues in total if the matrix is n by n. So let's assume that we have lambda 1 equal to lambda 2 equal to lambda 3 up to lambda k. So k of those, we call this k-fold degeneracy. K-fold degeneracy. K of the eigenvalues, n eigenvalues, are equal, so we call them k-fold degeneracy. And lambda k plus 1, lambda k plus 2, up to the rest, which is lambda n, are distinct. So in this case, I can still write the eigenvalue problem A xi equal to lambda xi. But in this case, from I equal to 1 up to k, what should I write for lambda? So from 1 to k, all lambdas are the same. So I can pick up here just lambda 1, because lambda 1 is equal to lambda 2 is equal to lambda 3. So from I equal to 1 to k, you can write axi equal to lambda 1 xi. This is not I, this is lambda 1. So you can write lambda 1 or lambda 2 or lambda 3 or whatever. So a linear combination of the eigenvalues xi is also eigenvectors, was lambda equal to lambda 1. So in order to prove this, so if you have a linear combination of the eigenvectors xi, those linear combination also will be an eigenvector. So to prove it, let's assume that the new vector that we form from xi's is called z, and this is from I equal to 1 up to n. So if you try now to do the eigenvalue problem, A multiplied by Z equal to A multiplied by Z is just, we'll get it here, summation from I equal to 1 to n Ci xi, get I inside, A inside. This will give you summation of Ci A xi, I equal to 1 to n, and then what's A xi? Ci lambda 1 xi, and this will be equal to what? Lambda 1 will be outside, summation of Ci xi, and what's summation of Ci xi? Is Z again. So you will end up with A Z equal to lambda 1 Z. And actually, this should run, you did not correct me, this should run from 1 to k, because only lambda 1 is from 1 to k, not from 1 to n. So you did not catch it. So xi's from I equal to 1 to k, they are not mutually orthogonal. Why? x1, x2, x3 up to xk, they are not mutually orthogonal. No, because the condition for mutually orthogonal is we got the condition was what? Lambda I minus lambda j xi xj equal to 0. The condition that xi's are mutually orthogonal is I have distinct values for lambda i's. Yes? But if I have degeneracy, this means that the lambda i's are what? Are equal, identical. So in this case, I cannot say that xi's are what? Are mutually orthogonal. Is there any way that I can form mutual orthogonal vectors if I do not have those vectors mutually orthogonal? Yes. There is a technique or a method written by Graham, Schmidt, orthogonalization. So how to orthogonalize vectors that they are not mutually orthogonal. So simply we'll take the first vector is x1, and it is one of the vectors that are not mutually orthogonal. And I will call the new vector set of vectors z1, and z1 will be the new set of vectors that will be mutually orthogonal. So what you will do is you will take z1 equal to x1, z2 will be equal to x2. If I say just equal to x2, I did not make anything. Yes, because I will continue here up to the k, xk, and I will pick up the same, I will have identical, the same. z1 is equal to x1, z2 is equal to x2, and so on. I did not form a mutually orthogonal vectors. So I have to subtract from this the projection of the vector x2 on the vector z1. So how to do it? So this will be, I will take a unit vector in the direction of z1, and I will get the inner product of the vector x2 with this d1. So this will be, this is what? Projection of what? Projection of x2 on z1. Then I will multiply this by z1. So this will be a vector, a new vector in the z1. Yes? And I will shoot you in a minute, but let me continue the rest. These three will be x3 minus z2 x3 z2 minus z1 x3 z1, and what's zk for those non-orthogonal vectors? This will be xk minus zk minus 1 xk in the direction of zk minus 1 minus 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 until you reach to z1 xk z1. So somebody will say, okay, how we will do this? Let's assume that I have the set of non-mutual eigenvectors are only two vectors, x1 and x2. So I have, let's say, n by n matrix. Two of those eigenvalues are equal. So lambda 1 and lambda 2. And lambda 3 up to lambda n, they are distinct. This is degenerate. So how many eigenvectors from here? 2, which is what? x1 what? Are they mutually orthogonal or not? No, because the eigenvalues are what? Equal. But for here, not mutually orthogonal. But x3 up to xn are mutually orthogonal. Now, how to get from x1 and x2 are not mutually orthogonal, how to form a new set of vectors that are mutually orthogonal. This is what Gram-Schmidt method will tell us. So here is, concentrate in this. This is, let's say, vector x1. And this is what? Vector x2. Are they mutually orthogonal? No. So first step is z1 equal to what? x1. Okay, guys? I want you to focus with me here and stop writing until you understand this. So z1 equal to x1. So where is the vector z1? Same. So this is z1. What's z2? x2 minus the projection of what? The projection of z2, projection of x2 on z1 multiplied by what? z1. Let's look at this. What's the projection of x2 on z1? This is the projection. So this is what? This is z1 unit vector dot product with x2. So this is just the amplitude. Yes? If I multiply the amplitude by the unit vector z, this will give me a vector which is this one. Yes, guys? Yes? What's the negative of this vector? Would be in the opposite direction. So this is z1 and this is what? z1 x2 in the direction of z1 but in the negative here. Yes? So now what's this? x2. So now what's this? What's this? This is what? z2, which is what? x2 minus, this is x2, and this is minus what? Minus this. x2 minus this. x2 minus this. Yes? And this gives me what? z2. How did you see z1 and z2 now? Mutual orthogonal. So if you have 3 vectors, you will do the same. 4 vectors, you will do the same. K vectors, you will do the same. So this is how we will do the technique here. Gram-Schmidt. So now, we talked about normal matrices, and we showed that the normal matrices, some of those normal matrices like Hermitian, anti-Hermitian, and unitary, and then we looked at the eigenvalues for those matrices. Today we looked at the eigenvectors, yes, and we stated that if you have for the values, if you have distinct eigenvalues, you will have what? Mutually orthogonal eigenvectors. If you have equal eigenvalues, so this is called degeneracy, and you will not have a mutually orthogonal eigenvectors, but still using the Gram-Schmidt method, you can form what? A mutual orthogonal vectors. Yes. So for normal matrices, I can form easily a set of mutually orthogonal vectors, and I can take those as the basis of the normal matrices. Now, what about non-normal or general matrices? So general matrices, they have some properties. First of all, no general properties for their eigenvectors or eigenvalues. They are not like the normal matrices. So for normal matrices, we saw that there is some general properties, like what? They are real. For Hermitian, for skew Hermitian, they are what? Pure imaginary or zero. Or for unitary, the eigenvalues are what? Lambda square for the amplitude equal to 0. And for the eigenvectors, they form what? Orthogonal set of vectors. But for n by n non-normal matrices, and how many are there in the universe? A lot. But the most important ones are the normal matrices, and this is what we'll be studying, because if you look at engineering application, science application, scientific application, cosmology, anywhere you study those types of matrices, you will encounter a lot, the normal matrices. This is why we keep talking about normal matrices almost for now 3 or 4 lectures. So the first thing is no general properties. Generally cannot find orthogonal set of n eigenvectors. They are not like, even you will be lucky if you find pairs of eigenvectors that are mutually orthogonal. 3, if you have n by n matrix with distinct eigenvalues that has n linearly independent eigenvectors that form a basis for n-dimensional vector space. And finally, if degenerate eigenvalues occur, so there may or may not be n linearly independent eigenvectors, vectors, and if we have less than n linearly independent eigenvectors, the matrix A n by n will be called the effective. So if you have a matrix A n by n and you cannot find, you have less than n of linearly independent eigenvectors, so in this case we'll call the matrix as defective. So I will stop here, and next time we'll go through the simultaneous eigenvectors and we'll move on to the next topic. So we'll still be working also in the matrices, and hopefully by lecture 17 we will be done with matrices. So now we are in lecture number, today's lecture number 13, I think. So yes, there's 3 more or 4 more lectures in matrices, then we'll be done with matrices and move to chapter number 11. Thank you so much. Do you have any questions? Okay, thank you so much.